Allora, buongiorno a tutti. Good evening, good morning, good afternoon, everybody, wherever you might be. Today we are very happy to have a local speaker from Italy, originally, now from Warsaw, JACOPO BASSI, and he will tell us about isometries for spectral triples on approximately finite algebras. It's all yours. Take it away.
Thank you very much. Thank you very much to the organizers for the invitation. It's a pleasure for me to give a talk here during my last days in Warsaw. The topic I want to cover in this seminar is about the study of particular groups which are naturally associated to spectral triples, which are non-commutative analogs, groups. Natural generalizations of groups of isometries. And so already Carla Parsi gave a talk here, I think 3 weeks ago, about this topic. She covered really a very large amount of stuff related to this. She gave really an overview of what are the results that we obtained up to now, what are the possible directions for future research, and so on. So while preparing this talk, I was thinking about really specializing to some examples to see how things work in particular cases. And in particular, I think it would be useful to look at the easiest case, let's say, that is the case of air algebras. This is based on a joint work with Roberto Conti for what concerns all the study of isometry groups on AR algebras, in particular associated with spectral triples introduced by Christensen and Ivan. And in the last part of the talk, I would like to talk about how these constructions fit into the framework of quantum Gromov-Hausdorff convergence, as was introduced by Ruffel and then developed by Latremouille. So let me start with some definition, just to fix the notation and be sure we speak the same language. Now, everyone here knows better than me what a spectral tripole is, but let me recall it. So spectral triples were introduced by Alan, and in order to give really a smooth version of Gelfand duality. So Gelfand duality is the fact that if you have, for example, a compact outer space, the topology of the space is can be detected by looking at the C-star algebraic structure of the continuous functions on the space. Now, one of the things that Kohn understood is that if you start, for example, with the compact Riemannian-oriented manifold, and you want to reconstruct not only the topology, but the metric, in order to do this, you can consider some more information. And the information you need is a particular representation of the continuous functions on the space. For example, you can take the action by multiplication on if you have a Riemannian manifold, you have a measure, and so you can consider the L2 complex forms on this manifold. And you have by multiplication there with continuous functions. And the idea is that in order to reconstruct the metric, you have to look at the way the representation of the continuous functions is related to the action of a particular operator, that is the de Rham operator. So this led Kohn to the definition of what is called the spectral triple. And this is also important, of course, in KK theory and in abstract situation, the situation in which the C-star algebra is more general, this is given by the following definition. So we start with the unital C-star algebra, which is represented faithfully on a Hilbert space. And we suppose that on this Hilbert space we have this particular operator that is called the Dirac operator, that is an unbounded self-adjoint operator. Now, we consider the algebra, the set of elements in the algebra, such that they leave invariant the domain of the Dirac operator. Such that the commutator, so since they leave invariant the domain, it's possible to consider the commutator of these elements with the Dirac operator, and we want that this set has the property that the commutator extends to a bounded operator on H. So we consider this particular set, and we want that this is dense in the sister algebra. And this is the analog of Cauchy's function, so smooth path. The Dirac operator to satisfy a particular that is the fact that the compact resolver. So 1 plus d squared to the minus 1 should be a compact operator. So this is the definition of the spectral triple. And so now, as I said before, Kohn understood that you can reconstruct the metric in particular classical cases. Now, the way you reconstruct the metric is by a particular formula that you can use for every spectral. So for every spectral group, you can define a pseudometric in general that is given by the Dirac operator. And this is a pseudometric of the state space of the unital sister. And this is given by the following. You take two states, phi and psi, and then you want to compute the sum of the absolute value of pi of A minus psi of A computed over the set of elements in the sister algebra, such that they have bounded commutators with the Dirac operator. The norm of this commutator is less or equal to 1. So, Parker in 1995, he basically had the following idea. He said, okay, so for classical cases, the metric is really something that can be reconstructed by functional analysis. You have to look at the particular representation, Dirac operator in the space, and we can see the metric inside this information. So in principle, we should be able to reconstruct also the group of isometries to the depth, the group of isometries by functional analysis.
Sorry, just a historical question. Who was this guy, Gao E. Park? I've never.
Let's compare.
Yeah.
You know,
University, whom.
Yeah, I don't remember.
I never said time, and it's 95, so it's like at the beginning of the story.
Yeah, honestly, I didn't check.
Okay.
Yeah, sorry. So, but yeah, so what we understood is that if you look at the classical case, for example, the case that I said before, when you look at compact Riemannian-oriented manifold, you can reconstruct the symmetry group in this way. You have to consider the automorphism of the sister algebras. Of course, it will be a subgroup of the automorphism, since these are the self-homomorphisms. And then should be unitary implemented inside this. No, it's another one.
It's another one.
It's Fton.
Fton.
Yeah. So you have to look at the automorphisms of the sister algebras, which are unitarily implemented inside this Hilbert space, and among all the possible unitaries which implement the automorphism, you should be able to find one that commutes with the Dirac operator. So this group of automorphisms is actually a group of isometries in the classical case. And this is what inspired the definition of what I will call the small isometric group of the sister algebra, of the spectral triple. Now, there is also another natural definition of isometry that is really natural when we see at the corners. So we just take this pseudometric, the pseudometric induced by the Dirac operator on our spectral triple, and we say that the big or the large isometric group is the group of automorphisms of the sister algebras, such that whenever we take any two states on the sister algebras, we consider the precomposition of the states by the given automorphism, and there's the invariant under this the pseudo distance given by the Dirac operator should be left invariant under this precomposition. So these are
I have a question.
yeah.
So there are two definitions.
Yes.
The answer to the question is every isometry in the sense of the second definition can be expanded to can be implemented by a user operator. Do you have
No, in general, no.
No.
In the classic cases, yes. In the classic, I mean, if you look at the proof by a compare, he actually proves that.
What was the minimal counterexample?
I will show you. In a moment. So, and this last definition was for what was given by Roberto Conti and Stefano Rossi in the 2012. And this is the next. So in classical cases, it's always the case. I mean, this is always the case that the smallest group is a subgroup of the largest group. And this was proved by Carla Parsi during her talk. Now, as soon as we leave the commutative setting, the easiest possible spectral triple that we consider doesn't satisfy this. And I will show in a minute. So consider the sister algebra by two complex lattices, and consider a Dirac operator that is just given by a diagonal operator with two positive different eigenvalues. Consider the algebra acting on C2, on two copies of the complex numbers, and let's say that the small isometric group is actually strictly contained in the large isometric group. Why? Well, consider the following automorphism. The one that is unitarily implemented by this particular unitary. So this unitary is going to be like this, right? This 0. Here there is -1, but it's the same with 1. So we take this unitary, and we consider the automorphism implemented by this. Now, it's easy to verify that this automorphism, this unitary, doesn't commute with the Dirac operator. Now, if you take another unitary implementing the same automorphism, since the 2x2 matrix is a simple sister algebra, the only difference between this and another unitary implementing the same automorphism is a multiple of the density. So in particular, there is no unitary implementing this automorphism which can commute with the Dirac operator. Now let's see that this actually preserves the condistance. So compute the distance between phi composition that joint action of U and psi composition that joint action of U. So this is the sum of phi of UAU star minus psi UAU star, absolute value, over all the elements in the sister algebra for which the commutator with the Dirac operator is norm less or equal to 1. So we do a simple change of value, and this is the sum of phi of A minus psi of A over all the elements for which the norm of the commutator of D with U star AU is less or equal to 1. And now it's really a simple computation that is the following, that the commutator of D with U star AU is equal to minus U star commutator of D with AU. And this is just a computation. In particular, they have the same norm. And so actually, this is an element of the large isometric group. So as soon as we leave the commutative setting, we expect that they are different.
Sorry, may I have a question?
Yes.
So, if this isometry doesn't commute with the Dirac operator, so it means in a sense that it is not small.
Yes.
So it's some topological phenomenon, some geometric phenomenon.
Yeah, I don't really understand, but it's exactly the point. It's not book, but it preserves this consistence. And this is really the point, in my opinion. It's really that here we have a simple system algebras. And so these ideas have to be well understood, right? It's not like in the commutative setting. By the way, yeah, it's a good point. Okay.
Sorry, may I have a question, but not to the speaker, but to the Zoom audience about sound quality, since I don't know whether it's only me, but I can hardly hear what has been said.
I'm also having the same issue, I think. It's a bit like an echo, right?
So the sound quality seems to be quite poor.
Yeah, but I'm not sure there is much we can do about it.
Yes, me too. I have problem in the quality of the voice.
So the proof was very detailed in the slides, so I can follow, but just the sound quality.
And the microphones are here. One, three, four.
Okay.
I mean, and how about us? Are we also, we cannot hear us?
For you, Piotr, it's fine. For Tomasz, maybe a little.
But I'm
worse.
close to two mics.
But this is a bit crazy because JACOPO is next.
Close
There's nothing more I can do.
Maybe the echo is because
Piotr,
you have
even
more
when
than
you're
one
speaking,
microphone, they
your
have to
voice
go.
disappears.
So that's
When
new.
you're
I mean,
speaking, when you were speaking, your voice was fading. So there is something wrong.
Yes, it definitely, the sound quality is definitely inferior than the previous times. It's not the same.
Maybe the
okay.
microphones are too close.
Now I moved microphone close to me. So now, how do you hear me now?
Better.
Okay.
No, better, yeah.
So that's fine. So okay. So the only thing I can suggest.
If I speak here,
Yeah. How about now?
is it better?
I think
Yes,
so.
that's better. Yes, that's better.
Okay, I will try to speak here, but I don't know if I can look at my slides.
You can
I can
But
move
just a
it.
You can
yes,
move.
but I have one mathematical questions on the talk. I would like to ask: is commutativity of algebra equivalent to the coincidence of the two isometric group? Because
The other way around.
Yes. I mean that is it true to say that an algebra is commutative if and only if the two notion of the isometry is the same?
Oh, this is a very good question. Well, I don't know the answer. Honestly.
Probably not, because there are even classical spaces with a very small isometry group. Classical isometry group.
Yeah, I don't know the answer. There is a special case in which they proved that the two isometry groups are equal for non-commutative sister algebra, but in that case, you don't really have a spectral triple in the classical sense because the resolvent is not compact. Something lighter.
It's like almost a counterexample.
Yeah. But I don't know. Yeah, this is a very interesting question.
Okay.
Yeah. Thank you.
So can I ask another question? It's about the classical case.
Now, Francesco, we can hear you very badly.
What about now?
Perfect. Yes.
Okay. So no, in the classical case, because I remember these works by Goswami, Jyotish Bhaumik, and I mean, what I remembered is that still you should not have the same group because the distance depends only on the square of the Dirac operator, right? Only on the Laplacian.
No.
So it depends
No.
on the Riemannian metric and not on the spin structure. So things commuting with the Dirac operator should give you something smaller also in the classical case, right?
Yeah, it could be. It could be. I mean,
no, because you say there is this result by Park saying that classically they are the same, but
yeah, what he considered is the following situation. You take a compact Riemannian-oriented manifold, you have a natural measure associated to this, and you consider the complex L2 forms.
Okay.
If I may say something, Francesco.
Yes.
Answering you, the distance, the Const formula for the distance depends on the Dirac operator, not on d square.
But classically, it depends only on the metric, the Riemannian metric, not on the Riemannian, on the spin structure. And the Riemannian
yes,
metric
it depends on the metric because, I mean, in the classical case, I mean, what you add, I mean, it depends only on the principal symbol of the Dirac operator. What you add to the Dirac operator doesn't really matter. This is not the case in the non-commutative. In the non-commutative situation, you add a small thing to the Dirac operator, which doesn't commute to the with the algebra, and it changes the distance formula.
Ah, okay.
And also it changes, I mean, by the way, it also changes, you know, the things that commute with the Dirac operator. So, you know, the notion of isometries, I mean, like something like preserves the metric, I mean, first, I mean, requires, you know, understanding the metric.
Okay, thanks.
Sure, yeah. So, okay, thank you very much for the very interesting comments. So up to now, what we know, I don't know if this is really all the results, but okay, the first result was by Park, Efton Park gave this characterization in the classical case, and also studied spectral triples on reduced group C-star algebras, and he could obtain some result about the structure of this small isometry group, in particular that it is a compactly group. Later on, Long and Wu studied also twisted reduced group C-star algebras, and they really obtained very good results about the small isometry group. They obtained really the group itself, that it was like a certain semi-direct product. Later on, Roberto Conti and Rossi studied certain spectral triples on Kunz algebras that were introduced by Mesland and some other collaborators, and could find the structure of the small isometry group, and studied also some other variation, as I said before, some weakening of the notion of spectral triple, that were constructed by Tomita Takesaki theory associated to certain KMS states, and could prove that in those situations they obtained the equality between small isometry group and large isometry group. Then Conti and Farsi, they studied spectral triples that were introduced by Kellendonk and Savigny. And so these spectral triples are spectral triples constructed on continuous functions on boundaries of trees, in which you have a sort of length function, let's say, which gives rise to a Dirac operator, and understood the structure of the small isometry group. Me and Conti studied the case of spectral triples on AF algebras constructed by Christensen and Ivan. And now a very recent paper that I think it was accepted some days ago in IMRN by Dimitris, Goffeng, and Mesland. They computed the small isometry groups of certain spectral triples on Kunz-Krieger algebras using really the fact that this can be realized as groupoid C-star algebras, and then starting from a Dirac operator on the base space, they could construct a Dirac operator on the groupoid, and they really found the structure of these isometry groups. So these are some results up to now. So let's go.
Sorry, I have a question. How big is this subgroup of Park in this bigger isometry group?
Which one? Sorry, for the reduced group sister algebras? For what?
In general, if you think about these two models for isometries.
This is something that is completely unknown. And this is something, indeed, in my talk, what I want to, one of the messages is that while the small isometry group is something that really you can compute, usually. If you work a lot, you can compute it. The large isometry group is something that you don't know anything. And indeed, the part of the study that we did with Roberto Conti was really to say, okay, we have certain automorphisms that we know are not in the small isometry group. Can we prove that they are not in the large isometry group? So just to say that certain automorphisms are not in the large isometry group is something very difficult to do. So this is a question that, I don't know in general.
Even such natural questions like, is this Park's group a closed subgroup in this bigger one?
Well, okay, you have to specify some topology. Now, this is something that we studied for example, with Farsi, La Tremolier, and Conti. And if you give a certain topology that is called, you have to introduce a metric that is Monge-Kantorovich metric, then it is possible to prove that this is a compact subgroup of the large isometry.
What about compactness of this big group?
It's also.
It's also. So
compact. Yeah.
Oops.
And this was important also for Gromov-Hausdorff conversion, because you have really to understand some topological stuff.
And what about normality of this smaller group?
Yeah, this is something we don't know.
No, they have a constant. Outer.
Yes.
So, okay, the last bit of information. So we just say that if we have a spectral triple, we say that this is a metric spectral triple if the con distance is actually a pseudometric, is actually a metric, and the topology it induces is the weak-star topology on the state space of the sister algebra. So this was a concept that was introduced by Riffel in the context of quantum compact metric space. Now, okay, we have all the information. Let's start with considering Christensen-Evans spectral triples. So we start with the, I don't know if they will. We start with the AF algebra, a unital AF algebra. We take a faithful state. We fix, this is very important, we have to fix a direct limit decomposition of the algebra. So if you choose a different direct limit decomposition as increasing union of finite dimensional sister algebras, you obtain something different. And we fix the A0 should be just the multiple of the identity. Okay, so we can take the GNS construction associated to the faithful state, and we can consider, so we have this Hilbert space, big Hilbert space H, and we can consider truncations of the Hilbert space given by the finite dimensional approximants. So they are just the span of elements of AN, let's say, applied to the cyclic separating vector. Now, we have projections for each n. Pn is the projection from the large Hilbert space of the GNS associated to A to the restricted GNS associated to AN, and we consider the difference between these two projections in such a way that we obtain orthogonal projection, and we fixed Q0 that is equal to just P0, the multiple of the identity. Now we take any diverging sequence of real numbers, and we impose that lambda 0 is equal to 0. And also, I didn't write it, but we impose also that this is the only one that is 0, and this is important. And now we can consider the Dirac operator that is given by the sum over n of lambda n Qn. So an important result that is actually not difficult to prove by Christensen and Ivan is the following, is that if the sequence lambda n grows fast enough, then we know that there is a summable sequence beta n in L1 of the natural numbers, such that for every A in the C-star algebra, when you consider the norm of the difference between En of A and En plus 1 of A, where En is the conditional expectation on the finite dimensional approximant An, this is less than beta n times the norm of the commutator of D with A. And it's interesting that we know that it's true, but we don't have a way to understand how fast this should go. We know that if it goes fast enough, it is the case. And they proved that in this case, the spectral triple we obtain is a metric spectral triple, based on a result by Riffel. And really, this result comes from the fact that we have a finite dimensional approximants. This is based on the fact that any two norms on a finite dimensional linear space are equivalent. So this is really important that we have AF algebra.
Sorry, to be sure, in your limit, direct limit of finite dimensional algebras, do you assume that all they are unital and they share the same unit?
Exactly. So yeah, A0 is just multiple of the identities, and all the others have the same identity. Yeah, this is important.
And sorry, somehow I'm lost. This En is what? Could you remind me?
En, yeah, maybe I can try to write, but I don't know if you can hear. Let's try it. So it's given by the following. So you have now you send A to A psi phi. Psi phi is the cyclic separating variable. Now you apply Pn. Now this is an element of Hn. So since the vector is cyclic separating, this element should correspond an element in N of A. That is in An. This is the procedure we obtain this conditional expectation. Did you hear?
Okay, makes sense. Thank you.
You're welcome. So let me. Okay. So we take this case, this particular spectral triple, and tell you that in this case it's very easy to compute what is the small isometry group. And this is very different from the way to I mean, in the case of the large iso group, we can say very few, but the small isometry group is very easy to compute. So let's start with the spectral triple like the one that I defined before, that was given by Christensen and Ivan. Now, for every I, we define this term Ni, that is the max of k greater or equal than I, such that lambda k is equal to lambda I. So the point here is that we are not considering the case in which the eigenvalues are all different. We can also have that there are some blocks in which they are equal. And for each of these blocks, we take the natural number that is the last one, the bigger one that is equal to the previous ones. So the small isometry group is given by the group of isomorphisms of the C-star algebras, such that they leave every of the finite dimensional approximants associated to these Ni's, to these last natural numbers for which all the eigenvalues, for which is the last one. After this, the next eigenvalue is different. And such that this preserves under precomposition the faithful state we chose. So you see immediately from this that is very important to fix the inductive limit decomposition, because it gives different groups.
Sorry, I'm a little bit confused in your notation. So this Ni should be the index of those lambda. So, but in the proof, you assume in the case lambda I is equal to Ni. So
Yeah, I mean, what I mean is the following, that I only give the proof for the case in which the eigenvalues are all different.
yes, but still,
It's an
those are different
enumeration
eigenvalues,
of-
not necessarily the subscript of it. It's like
Sorry?
still, even if those are different eigenvalues, those are eigenvalues. So all they could be different from this index, and I is just a subscript, yes, of this eigenvalue, as you have written it.
Oh,
And
you're right. I wrote it in the wrong way. Yeah, you're right. I'm sorry. What I meant is that the eigenvalues are all different.
okay.
Yeah, sorry. So, yeah, let's suppose that the eigenvalues are all different. So, first of all, let's see that the small isogroup is contained in the other.
So what you meant is that lambda I is equal to lambda with subscript Ni, probably.
Yes.
Yeah?
Exactly.
Okay.
Yes. Thank you. Yeah, sorry. So let's prove that in this case, these two groups are the same. So first of all, let's prove the inclusion of the small isogroup inside this other group on the right. So let's start with an automorphism, which is unitarily implemented by a unitary in this Hilbert space, which commutes with the Dirac operator. Since this commutes with the Dirac operator, it leaves invariant all the eigenspaces, and in particular, it will leave invariant all the truncations, HIs. So in particular, it leaves invariant the eigenspace associated to lambda 0. And so this implies that at least phi composition alpha is equal to phi. Moreover, for every I and element of the approximant AI, we have that UAU star psi phi is an element of HI. And since psi phi is separating, we have that the UAU star is in AI. And so we have showed that this should leave invariant all the finite dimensional approximants. And so we have an inclusion of the small group inside the second part. So let's see the inclusion of the second group inside the first group. So let's start with alpha, which is an automorphism. We satisfy the condition on the right. So it leaves invariant every finite dimensional approximant and leaves invariant the faithful state. Then if we consider the linear map, we send AX psi phi to alpha of AX psi phi. This defines a unitary on this Hilbert space. And this unitary is very easy to see that leaves invariant every HI. And so in particular leaves invariant the image of QI for every I. And so commutes with the Dirac operator. So this is a very easy computation which shows which gives really the structure of the small isometry group for these particular cases. Now, in particular, let's see some particular situations in which we start with the UHF algebra. So let's suppose A is the infinite tensor product over I of M and I, and suppose that the lambda i's are strictly increasing. Then the isometry group is the group of automorphisms of the sister algebras, which can be written as a tensor product of automorphism alpha I, where if H alpha I is an automorphism of the simple matrix algebra M and I, and such that phi composition with alpha is equal to phi. This is because if an automorphism leaves invariant every AI, then it leaves invariant also the commutant. In particular, if you have a product state of the form tensor product over I of phi I. Then the symmetry group is again the group of tensor product of automorphisms, such that each of the automorphisms alpha I should live invariant the component phi I of the state. And this is just the product of the unitary groups of level Ni, such that under the adjoint action of these unitaries, phi I is left invariant, quotient by the natural equivalence relation that is two automorphisms define, two unitaries define the same automorphism if and only if they differ by a phase. And in particular, if you take phi, that is the trace, then every of these unitaries UI will live invariant under the adjoint action, the state phi I, that is the trace restricted to the simple tensor factor. And so the isometry group, the small isometry group, is just the product of unitaries at the level Ni over S1. So,
sorry, a question.
Yes.
So what is divided by the action of S1?
Yes.
All product or every or
Each one.
Each one.
Each one.
So,
Yeah. So, okay, we have a very neat description of the small isometry groups for UHF algebras. And now I want to try to see what we can say about the large isometry group. Now, later on, we will see something else about small isometry groups for other AF algebras. But for the time being, let's stick to the UHF algebras. And already excluding automorphisms from the large isogroup is not an easy task. So let's see, for example, what can I say? So already one could ask, is it true that the large isogroup is different from the whole automorphism group of the sister algebra? And this is certainly, I mean, it's something we expect that this is not true, but you have to prove it, right? So what we can say is the following. Suppose again that A is a UHF algebra and take the trace on A. Suppose that lambda I is a sequence of eigenvalues of the Dirac operator.
How do we know that there is a unique trace on A?
Oh, because it's a UHF algebra.
Oh, yeah.
Yeah. So take the eigenvalues of the Dirac operator associated to a Christensen-Iwan spectral triplet that grow fast enough. Grow fast enough, I mean that the condition I showed you before is satisfied, this condition. So we have a metric spectral triple. Okay. So I tell you the following, that if you look at the outside the large isogroup, but inside the automorphism group of the sister algebra A, here there is at least a countable union of copies of the large isogroup. So there are some automorphisms that are outside. So let's see how to prove that the large isogroup is different from all the automorphism group. And this really uses some very deep results that are in the literature. So,
if I could interrupt, I'm again.
Sure, please.
Again, I'm a little bit confused by this notation, since okay, you have written that there is a inclusion, but okay, the right-hand side is not a group. You just throw out something.
Yeah, exactly. So, what I'm trying to say is that in the case of the large isogroup, it's very difficult to understand how to deduce the structure. And so what we try to do is to find ways to say that this is small, at least in a certain sense. And in this case, I'm saying that outside the automorphism group of A, there are at least this many elements. Outside the ISO group, there are at least this many elements that are automorphisms, but are not in the large ISO group.
Okay, but one cannot read this inclusion literally, yes? As really being a subset.
No, this is just an inclusion of sets.
Yeah.
What I'm saying is that I don't know. There is one set with this cardinality that is there.
Okay, so there is a set theoretical embedding. So an injective function from the left-hand side to right-hand side. Yes.
Exactly.
Okay.
Yes.
That makes sense. Okay, thank you.
Thanks.
What about rewriting this in terms of topological groups? So, because you are subtracting this ISO on the right-hand side, you are embedding this countable union of copies
Yes.
on the left-hand side. So it's so intermingled.
Yeah. No, this is not about the group structure. This is just about the fact that.
But ISO is a subgroup of tomorrow.
Sure.
No, but Thomas, but the right-hand side is not even a group. You throw something out.
Exactly.
I told it.
Okay.
Exactly. This is my point.
Yeah.
So I would like to understand how the subgroup ISO in automorphism is situated.
So
Maybe
Thomas,
something about the countable number of cosets of something. I don't know.
So probably you have the same problem that I have had, but okay, as it was explained, probably it should be understood in the following way that the left hand there is an injective function, but only set theoretical function from the left hand side to the right hand side. So not being a strict inclusion, literal inclusion, but also not being a subgroup, but also not having a embedding of subgroups, since in the right hand is not a group. So just an injective map, a set theoretical injection, and nothing more.
Yeah.
Even restricted to every component of the left-hand side, it is not like embedding into a group. No.
Right-hand side is not a group, Tomasz.
Yes, I know. I'm talking about the components. Every component is okay. So I was asking how these components are laying inside of this object. They are not cosets.
Cosets.
They are cosets. Cosets. Cosets.
Yeah, if I remember correctly, they are cosets. Yeah.
Okay.
Yeah.
It's this.
Yeah.
Okay.
So let's just see that there is at least one element that is outside the
JACOPO, hi.
large.
JACOPO, can you hear me? Ludwig, hi.
Oh, hi, Ludwig. Yeah. Sure.
So, yeah, that's interesting. I mean, this is a subtraction, this is set minus on the right-hand side?
Yes, exactly. This is minus. This is minus. Yeah.
This means that if you subtract one copy of isometry, there are still uncountable number of its copies in the rest. That's what you want to say. Okay.
Exactly. This is what I meant. Yeah.
Okay. But this doesn't tell us much because, I mean, there is a counter plus one in automorphism then, okay. So does it mean that there is n plus one natural numbers copies of isometries in automorphism? That's what you want to say? What does it mean to subtract this iso?
Well, it is a subgroup, so you're subtracting it. It's a theoretical subtraction.
Yeah, but this set is also on the left-hand side. It's ISO, so this ISO on the left side is identified with ISO.
I'm sorry, I confused everyone with No, what I wanted to say is that take the automorphism away and take this subgroup that we know how it sits inside the automorphism away, that is large ISO. Now, we are trying to say, is there anything outside the large ISO that is an automorphism? Yes, I say yes, there is at least one. And then after I find one, I say, okay, but maybe I can find more than one. And this is how many I can find.
What you need is that the left-hand side is non-empty, but actually during the proof, you find out that it's a lot more.
Yeah, exactly.
Is it different from saying that there are countably many co-cosets of ISO inside of automorphisms?
Yeah, I think this is true. Yeah.
Okay.
So let's just see the fact that there is one. Let's just see that there is one. So By assumption, we know that the pseudometric is actually a metric and gives the weak star topology on the state space. Now, Powers proved in a very deep paper that the action of the automorphism of A by precomposition on the pure states is transitive. And also, Gleam proved that the pure states are weak star dense in the state space of A. But then we start with the trace. Now, if you precompose the trace with any automorphism, is fixed because it's unique. And every automorphism gives another trace. So we look at the trace, we pick our favorite pure state, and we are sure that there is a sequence of automorphisms of the C-star algebra which will send this pure state towards the trace. And so at the end, the distance, the condistance between beta n applied to psi and tau should go to 0. So at least one at the end should not be an element of the large isogroup. And elaborating on this, one can find many more.
Sorry,
excuse me,
may
I have a
question?
question.
Sorry?
Yes.
May I have a
Yes.
question about this result of Gleam? I'm not familiar with it.
There is a paper.
And what are the assumptions of this theorem?
Oh, I don't remember exactly, but I think it's true for any UHF algebra.
I think it's not even.
You see, it sounds very strong since you have the result of how it is called, Krein-Milman theorem, but in the Krein-Milman theorem, you take convex combinations. So,
This is about density of pure states. It's very strange.
yeah, it's about
I
exactly.
agree.
You don't take any convex combinations and then take enclosure. It's just a closure of pure states.
Yeah, exactly. The weak star closure. Yeah, I don't remember honestly the proof by Gleam. I'm sorry.
Okay.
Yeah.
Okay.
But the paper is cited in my paper.
But sorry, but there are some assumptions on the underlying algebra, yes?
It has to be UHF, of course.
UHF, okay.
Separable, maybe. But I don't remember. I'm sorry. Yeah.
Okay, thank you.
So now, you see, from the, in the small isogroup, we have this description of the small isogroup for UHF algebras, in particular if we have a trace. And so we know instantly that the switches of the tensor factors, if we take something that is like a tensor product of all of Mn with the same n infinitely many times, we have a particular automorphism that are the switches of the tensor factors. And these automorphisms are not elements of the small isogroup. So we ask if they are actually automorphisms of the large isogroup. And this is again similar to the previous considerations to show that these switches of the tensor factors are not elements of the large isogroup. Why? Well, we proceed in a similar way. So we take A, that is, so in this case, the UHF algebra is just the infinite tensor product of Mn, where n is fixed. So we pick an element A in Mn such that the trace of A star A is equal to 1, and consider the shift homomorphism, sending x to 1 tensor x, and consider the vector state associated to phi k of A. So it's easy to see that this vector state converges in the weak star topology to the trace. And so in particular, the distance between the trace and the vector state associated to phi k of A goes to 0. And but now the vector state associated to phi k of A can be written as the vector state associated to A composition with the permutation between the first and the k plus 1 factor. And so we immediately obtain, just by writing this permutation as a composition of simple permutations, that there is a simple permutation moving I to I plus 1 that is not an element of the large isogroup. So you see, already to obtain that some elements that are not in the small isogroup are also not in the large isogroup, we need really to find some particular process. Now, what?
Sorry, I want to understand.
Sure, sure.
So this D, the Dirac operator,
Yes,
comes from n by n matrices. It's built with something which depends on mn.
yes, sure. It's I mean, we take so the approximate. So AN in this case is the tensor product. Oh, N is not a good AK, let's say. Is the tensor product I from 0 to K of Mn.
Yeah.
And so we do all the procedure that I described before. We take the trace that is faithful. We take the GNS representation, and this gives the truncations of the Hilbert spaces, and we construct the Dirac operator out of it.
So these truncations make this sigma not commuting with the Dirac operator.
Exactly. I mean, the small isogroup, you remember, it was really a product of the automorphism of every tensor factor. And so if we take this, of course,
But you are claiming more. It's not even in capital ISO.
Exactly.
But at least the fact that it doesn't belong to small ISO is clear.
Yes. So now one could ask.
Sorry, can you repeat again the argument why the sigma I plus is not in the big ISO? What's the argument again, please?
The argument is the following. So take the shift homomorph. That is this.
Okay.
Now, given this, I take A, that is an element of Mn, and I consider the vector state associated to phi k of A. Now, it's easy to see, you see, if you apply phi many times, you have something like 1 tensor 1, and so on. And so this means that this converts weak star to the trace. And so in particular, the distance between these two states goes to 0. But you can write these vector states as the composition of the vector state associated to A and the switch of 1 with careless 1. This is just the point, because then we have that this is composition, you see, this is given by this, and so it means that this is not an element of large ISO, because it doesn't preserve the constants by this.
That's the inequality.
Exactly. So at least we have found one of these switches of the tensor factors, which is not in the large ISO group. And one can ask, is it possible that there is some other of these switches of the tensor factors which is in the large ISO group? We are trying to understand if they're different, the small ISO group and the large ISO group. And in order to obtain this, it's actually, we could only obtain this in the case of the Car algebra. So the infinite tensor product of 2 by 2 matrices. Now let's see why. In order to obtain this, really, there are some, it's very technical and very long, but let's see some partial results in this direction. So let's start with A. There is a lemma before that works for every UHF algebra as before. So let's start with A, that is an infinite tensor product of MK, and again, we take the finite dimensional approximates that I described before. Consider a Christensen-Ivan spectral triple associated to the trace tau. And now I tell you the following, that if we take a vector in the Hilbert space Hn associated to the GNS for An, and we take the associated vector state, then when we want to compute the distance between this vector state and the trace, this is given by the sup of tau x minus phi v of x absolute value computed over a smaller set. That is the elements of the approximate AN with bounded commutator of norm at most one with the Dirac operator. So this is to say that if we take a vector state in the right Hilbert space HN, the constants is computed in AN. This is the lemma. So one second. So how do we see this? Well, it's enough to see that whenever you take an element X in this UHF algebra with the norm of the commutator with the Dirac operator that is less or equal to 1, then there is another element Y in the approximate AN such that this element also has the property that the norm of the commutator with the Dirac operator is less or equal to 1, and such that when we compute the difference, the absolute value of the difference tau of x minus 5v of x, this is equal to the absolute value of the difference between tau of y minus 5v of y. So this is clearly enough. And now, how do we find this element? Well, if you take x, now in the UHF algebra, the conditional expectation that I said before that there is for every F algebra actually has a very special form. And the special form is the one that I give here. That we send on simple tensor products, we send x1 tensor x2 tensor and so on, blah, 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 to x1 tensor x2 tensor, blah, 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 until we reach xn. And then we take the traces and we tensor by 1. So since the conditional expectation has this particular form, it's very easy to see that if you want to compute the norm of the commutator of D with the En of x, this is actually given by norm of Pn. So this will be norm of Pn absolute value commutator between D x Pn. So this is clearly less or equal than the norm of the commutator of D with x. And now, since we are taking a vector state coming from Hn, it's also easy to see that when we compute the absolute value of the difference, it is actually the same. So this is just a lemma to prove the result. Now, what is the result that we have in mind? So if we take the Car algebra, there are no permutations of the tensor factors in the large isogroup. Of course, we are always supposing to have this Christensen-Evans spectral triples associated to the trace. Now, you see that already in this situation, now, okay, I will tell about the proof in a particular situation. But the proof in general is based in the following. It's based on the following fact that we have to find particular vector states for which we can explicitly compute the condistance. And the vector states that we have to consider are the one of the form 1n tensor V. Now, where V is a certain 2x2 matrix of a certain manageable form, let's see. Now, let's see the proof in the case n equals 0. So we really take V, that is an element of the first approximant of this Car algebra. So it's in M2. And we proceed in the following way. We take an element X, that it will be the element on which we want to compute the soup. So it will be the variable when we compute the condistance. So we write it as a linear combination of Pauli matrices. And now we have to, we can really see the information that we have. And we can compute the norm of the commutator between d of x, it's easy to see that this is given by the following. Is lambda 1, that is the first non-zero eigenvalue of the Dirac operator, times the maximum between the norm of P0 x P1 minus P0 and the norm of P1 minus P0 x P0. So this basically means that if we write if the commutator of T with x, we write as an infinite matrix. In this decomposition of the GNS Hilbert space given by the projection Qn, this is something like this. It has all zeros on the diagonal, all zeros outside this, and we have only two elements, two non-zero entries, and these are the two non-zero entries. These ones. So we can compute explicitly the norm of this, and we see that they are greater or equal of absolute value of beta, where beta is the direction, the coefficient of the direction in one of the Pauli matrices. Moreover, we can compute explicitly also the norm of the commutator of B with the beta sigma 3, and this is given by lambda 1 absolute value of beta. So in particular, we certainly have that the norm of the commutator of D with X is greater or equal than the norm of the commutator with D with the sigma 3 direction of X. And now it follows from the lemma that okay, this is if we take this particular vector, this is just a fancy way to say this matrix 0 square root of 0 0. And now we try to compute the distance between the vector state associated to the matrix and the trace. So we have to, by the lemma, we should take the sup over all x's that now live in M2 of the absolute value of tau evaluated in x minus d evaluated in x. But now, as before, by the choice of this particular vector, we see that whenever we take x, we compute tau of x minus phi of x is the same as computing this other value by the choice of the vector state. And by what I said before, by this, the sup can be realized over this particular state. And since we can compute it, this is just given by the following formula, which gives lambda 1 to the minus 1. So at the end, for this particular vector, up to doing some lengthy computations, one can compute exactly the condistance between these two states. And elaborating on this kind of ideas, one can compute all the condistance between the trace and all the vector states of this form, 1n tensor d. And this is lambda n plus 1 to the minus 1. So this gives immediately that there are no permutations of the tensor factors which are in the large isogroup in this state. Now, this is what we could say for the UHF algebras, and you see that this is still is very few, but it's very difficult to understand the structure of the large isogroup in general. And this is very different from the small isogroup, in which immediately we could say everything. Now, let's get back to other AF algebras and consider commutative AF algebras. So we consider X, that is a compact Cantor set. I consider the canonical.
Wait, I'm confused. Isn't the Cantor set always compact?
Well, during the last years, there are papers in which they consider Cantor sets which are not compact. So I specify this. But yeah, usually Cantor set is meant to be compact. But I saw some paper in which they say the non-compact Cantor set.
The Cantor set, but with some funny topology, right?
Sorry?
Okay, the Cantor set, but with some funny topology.
No, they consider, I mean, this is, what is, totally disconnected and so on.
This is the product topology of.
In this case, yes. No, what I mean is the following. So the Cantor set has a particular property that is what is called is complete, metric, and totally disconnected. Is called something like this. You can consider the same, but not complete.
Probably you need also perfect, meaning no isolation.
Yes.
So
by the way, yeah, this is what we have in mind. And sorry. So consider the canonical AF structure. By this, okay, just to. So the structure is the following that you can realize the Cantor set is the following, right? You take the binary tree, rooted binary tree, and you take infinite paths on this. So this is the inverse limit, right, of the approximants. And so this is the topological characterization of this Cantor set. At the level of the system algebras, this immediately gives this particular inductive leading decomposition. So you fix at the level 0 just constant part on your Cantor set. At the level 1, we choose two Klopen complementary subsets, and we consider functions which are locally constant with respect to this partition. At the other level, we divide every of these two Klopen sets into Klopen sets, and this gives the structure of the continuous functions on the Cantor set. So we fix this. We fix a particular state that is the state given by the uniform measure on X, and consider a Christensen even spectral triple associated to this. Now it's easy to see that the fact, so by the characterization of the small isogroup that I told you before, that is, it has to leave every of the finite dimensional approximant invariant. It is actually the same as saying that in this binary tree, every level set will be left invariant. And so at the level of sets, the isometry group is this infinite copies of permutations of 2 elements, infinite copies of Z2. And if you look at the group structure, of course, there are some relations which give this infinite semidirect product. What is interesting is that in particular cases, for this spectral triples, we have that the large isogroup is equal to the small isogroup. And
sorry, could you explain this infinite semidirect product? So for finite, it means that further factors act on something before, okay?
Yeah, and this is
limits. You are taking a little bit lost. What is happening in
let me think.
Infinity?
Yeah, this is so you have every of this group that
limit.
Let me think.
In fact, I'm already confused at the level of 3 factors. I'm only familiar with a semi-direct product for 2 factors.
Yeah, but
no, what I mean is the following.
Look at the tree. Look at the binary tree.
Exactly.
So you see more X.
So what we have is the following. At the level, we have the possibility of having these automorphisms, yes, which respect the level. And now we have the same at every other, for all the level together. So an element of this as all these switches put together. And so you have to think I don't remember. We thought about this, either it is an inverse limit or the direct limit, I don't remember. But concretely, is the fact that you choose at every level this particular automorphism, and you have all together that move for the infinite paths. Okay. Yeah. So I think it's clear from this. So in particular cases, if we choose the eigenvalues that have a particular form, so lambda n should be gamma to the minus n plus 1, where gamma is smaller than a certain, let's say, universal constant, then it is possible to see that the large isogroup is equal to the small isogroup. And okay, I don't know if I have time to explain this.
Sorry, I'm a little bit puzzled by the exact value of this constant, 3 minus square root of 5. Is this somehow related to the golden ratio?
Yeah, I can tell you. Yeah, it's so the point is the following. This is based on something that Christensen and Ivan understood. Understood the following, that whenever you take this particular spectral triple on the Cantor set, you can do the following. You take consider two infinite paths, for example, this and this, and you take the first level, let's say M, in which these two paths are different. Now, Christensen and Ivan understood that whenever you take lambda n that is of this particular form, there are certain functions. Let's call them alpha and beta. So you see, here we have natural numbers that give all this. So call it m of xy for two different poles in the Cantor set. I understood that you have the following. You consider a certain function of n of xy that is. So these are functions from the natural numbers to the real line. One is always greater, beta is always greater than the other. And this gives, if you look at the image, so we have here the real line. Suppose we have here, why is not?
You should stay clear of the edge. I mean, edge with singularities. I don't know what happened. Maybe, yeah. Okay.
So here we have the value of alpha associated to two particular points, m of xy. Here we have the value of beta, and I understood that in this graph, here there is the distance, the point distance between x and y. Okay? Now, if you change, so you see, here you are evaluating alpha and beta on a particular natural number. If you change the natural number, these stripes would intersect. But now the length of the stripes is related to the magnitude of gamma. And if gamma is small enough, the stripes do not intersect. And this is the reason why you obtain this result, because then you are sure that if you move, you apply alpha to x and alpha to y, the fact that you move between two different levels is the same of the fact that you are moving the distance, the cone distance. So this is how this value appears, because it gives exactly the fact that the stripes corresponding to the image of alpha and beta of natural numbers cannot intersect. This is I hope this is clear.
Okay, I've roughly got the idea, but still I don't know why 3 minus square root of 5, this particular value. So this comes up in the calculation, or?
Yeah, this comes from the particular forms of the functions alpha and beta that they consider. Yeah. You have to solve an equation and you find this value.
So unless we know the exact form of this function, we cannot say what value of gamma would be this threshold, yes?
Yeah, and we know the functions. They wrote the functions in their papers, and one has to solve an equation and find this value.
Okay.
So let me use it.
So probably maybe something like a quadratic equation, yes?
Yes.
A equation which is maybe very similar to the equation for a golden ratio. Maybe, I don't know. I'm just guessing.
Yeah, I don't know. I don't remember, honestly, the equation itself.
Excuse me, I have a question. Excuse me, maybe I'm missing something, but at the introduction of your talk, you says that the two isometric groups are the same for commutative algebra. So if it's really the case, I don't see what is something special for this proposition, because C of X is a commutative
But this
algebra.
is interesting because, I mean, what I wanted to say at the beginning is that if you take a compact Riemannian-oriented manifold, you can construct spectral triples for which the two isometry groups are the same. Now we don't have a smooth structure, right? So it's interesting that...
Yes, not for continuous structure. It's your introduction was only about the case of a Riemannian manifold and the group of isometry, yes? Yes.
So if I could comment, maybe it is sometimes quite misleading that the term commutative spectral triple means that the underlying algebra is commutative, but plus the whole bunch of axioms. So this is very confusing, that usually commutative...
I think I said classical, not commutative.
Classical is much more than commutative.
Yeah, this is more less misleading.
Yes. Classical is commutative, which comes from a Riemannian structure.
Exactly, yes.
So
this is commutative, but not classical.
Commutative very often means that the assumption of the reconstruction theorem of Kohn are satisfied. So there are plenty of assumptions.
But it's equivalent.
Yeah, but I agree that the name classical would be better.
So commutative is classical.
Yeah. It's about the Dirac. Exactly. Now let me take this opportunity to clarify her Cantor. So you're right. I mean, there is in the literature a non-compact Cantor set, and it appears in the context of p-adic numbers. However, there is a proposition 2.6 which says that in fact this crazy-looking non-compact Cantor set is simply the usual Cantor set. I mean, ternary Cantor set. Okay, minus 1 point. So there is a much ado.
Yeah, sure.
Because you just take out 1 point from the usual Cantor set. But when it comes, if you want to use an indeterminate article A compact Cantor set, well, then you really can have plethora of different Cantor sets by taking something else out than 1/3. It turns out that when you change the proportion of what you take out, you obtain really different enemies. They have different, they no longer have measure 0 and so on. So
no, Piotr, I think that the situation is a little bit subtle. If you throw out 1/5, for example, and you do it on each step, you get the same Cantor set, topologically the same. But if you throw on each step different part of this Cantor set, then you can get something which is of positive measure.
Okay, I just briefly read it. So it seemed to me that it was just saying that you change the size of what you throw out, and you don't have to change it at every step. But it doesn't matter.
It doesn't.
Okay, fine. It doesn't matter. It means that you can modify slightly this construction, and then you can get really different Cantor sets. Okay, but all of them are compact.
And in fact, all of them are topologically the same.
Yeah, sure.
But they can different.
They can have different measure.
Positive measure. Right?
Yeah.
I was saying, right? This is what I was saying.
Sure.
Okay. If one really wants to consider a family of Cantor sets, it's in a different context. So I find this a non-compact Cantor set very bad terminology because
the compact Cantor set.
yeah, you are using the compact Cantor set, right? And because when you say A, you somehow make an allusion to all that stuff which we just discussed, which are clearly not considering. So when you say a compact, it's really misleading because it's you are just taking the standard Cantor set, and all the story about the variety of Cantor sets is irrelevant for you.
Yeah, I agree.
And this compact is going beyond compact. It's really taking out one point. So let's forget it. It's not anything.
Okay.
I have a question about this number. Adam was asking.
Yeah.
Isn't this number related somehow to self-similarity of this Cantor set? There's a fractal nature of the Cantor set. I don't know these functions, alpha and beta, so I don't know. But that numbers rise frequently when you are considering fractals. Out of dimension, all this.
Yeah, you're right. I didn't think about it. Yeah, sure, there is some connection. But really, how this they define this part that they have particular functions explicitly given, alpha and beta, which satisfy this particular property, because they computed the norm of the commutator of the Dirac operator with the projections on the Globen sets. But now your question, yeah, I don't know the answer, but certainly there should be a connection. Yeah.
By the way, Jacopo, I have good news. You have 3 minutes left for 11 slides. So you might consider somehow.
So, well, what do I do? Okay, so I wanted to talk about Gromov-Hausdorff distance in the algebras. I don't have the time. I can just say roughly what happens. So there is a notion of Gromov-Hausdorff distance for quantum compact metric spaces, which are generalization of spectral triples. And so this was formalized by La Tremollier-Riffel. So just the result. Okay, this gives to the spaces of quantum compact metric spaces a complete metric. And it's possible to see that for the unit ALEF algebras, the approximants, the spectral triples, let's say the quantum compact metric spaces associated to the approximants converge in this Gromov-Hausdorff distance to the spectral triple, to the quantum compact metric space structure on the AF algebra. And one can also put some groups acting and consider a covariant Gromov-Hausdorff distance. And it's a bit more tricky, and completeness it's a very tricky argument here. But what we can see in the case of UHF algebras, the quantum compact metric space structure reached with the actions of the small isogroups converge to the quantum compact metric space structure of the limit algebra with this proper isogroup. Okay, this is maybe I cannot.
How about the large isogroup?
The large isogroup. This I don't think we could prove this. No.
Maybe it is unstable.
I think that what you can say is that it converts to a compact subgroup of it. But yeah, we couldn't prove more. Yeah, I think so. Yeah. Okay, so thanks.
Milan. Okay, any more questions? Maybe from Zoom first. I don't see any raised hands.
Maybe I would like to ask.
Okay, go ahead.
So there was some result regarding this car algebra,
Yes.
classical anti-commutation relations. And what about CCR?
Oh, I have no idea.
It cannot
Okay.
be expressed in such simple form as an infinite tensor product of 2 by 2 matrices, yes, but
Where was it?
so not classical commutation relation, canonical commutation relation. Yeah.
So what was CCR? How do you write it?
Adam?
Sorry?
What was CCR? I don't remember.
The same relation, but using commutator, not.
But I mean the car algebra. I mean the infinite tensor product of 2 by 2 matrices.
Yeah, but you know there is a specific form how this algebra can be represented via
Sure.
some universal relations, and those relations are of the form when you are taking anti-commutators, and instead of anti-commutators you take commutators, you get CCR, but there are some technical details that there is no bounded representation of such relations, so you need to go to the so-called integrated form, Weil integrated form of this canonical commutation relation. So this is generated by two families of unitary groups with the relation very similar in spirit to the relation of noncommutative torus, sorry, but this concerns two infinite families of unitaries. And this algebra, it behaves differently from this car algebra, since, for example, it's no longer separable. So I don't know how much of theory can be applied to this setting.
Yeah, I don't know. I didn't think about it. I'm sorry.
Okay.
May I continue your question, Adam? I will borrow context. There's a family of deformations of commutative relations with a parameter. Okay, so for this bosonic CCR, from this bosonic to this fermionic, okay, you can have this family. So what about if you exclude this CCR Adam was asking for, and you are speaking only about this this part of this deformation different from this bosonic part? Are these algebras of your sort? Do you have this presentation in terms of products?
Yeah, I don't know. I don't remember.
Usually they are defined by means of how is it called? Spaces. Yeah. So I wonder how far you can mimic.
Yeah, this is a good. Yeah, this is a good point. Maybe looking from this other perspective, it's possible. But yeah, I didn't think about it. But it's a very
one.
Yeah,
some catastrophe could happen.
Yeah,
but for p smaller than 1.
Yeah, we never thought about it, but it's a very good good point. Yeah.
And somewhere in between there is this case p equal to 0 when this parameter is equal to 0.
Yes, Tomasz, you mean free case, yes? Like
yes, free case.
Yes.
Yeah, it's a very good point. Yeah.
What is happening there?
Okay, Ali.
Yes, thank you very much for your very interesting talk. The concept of isometry is a very interesting point. Just a question about this concept. In the classical case, for example, the isometric group of a round sphere acts transitively on the sphere. So I wonder whether it's a trivial question or it's a good question that one asks the same question for a perturbation of classical sphere. For example, for a non-commutative sphere, one consider a possible appropriate spectral trip and ask the question, does the isometric group act transitively in an appropriate manner and definition sense? Is it a trivial question to ask? Is the isometric group of a non-commutative sphere has a transitive action? I mean, that is this question already work? Is it a trivial question, or you think
No,
that
I think
it's a good
it's an interesting question. Unfortunately, this is something that I didn't look at these particular cases, but it's possible. I don't know, but it's possible. It's possible, sure. It's something that I mean, there are several cases. We are trying to do case by case, and this is one of the cases that we are interested in the next months.
But sorry, can you tell me again what exactly is this classical situation that the isometry group?
A compact Riemann-oriented manifold, and so you have the Riemannian structure that gives a measure. You take the complex L2 forms associated to this, and you have the continuous functions act by multiplication. Now, the Dirac operator is D plus D star, where D is the RAM operator. This is the situation.
Then you take the isometry of this.
Exactly.
Yes, but the rounded sphere is a very particular case because there are compact Riemann surfaces whose isometric group is finite. They don't act transitively. But since the rounded sphere is a particular case, so I'm not sure if the non-commutative analogy is obvious or not.
Well, I don't know. I think it's not trivial, the question. I think it's something one has to think about. Yeah.
Yes, I see. Thank you. And I have another question from Adam. He pointed out, I didn't understand well. Adam, did you say that it is always true that the convex combination of states, a convex combination of pure states is equal to the state space, or we need some other assumption? You pointed out to Krein-Milman theorem, and you say that under some particular assumption, or every time the closed convex hull of the pure state is equal to a state.
Yeah. So no. For Krein-Milman, the assumptions are very weak, but here the theorem which was used in this proof was very stronger, much stronger. You didn't take convex combinations as far as
boundaries.
But the assumption was very strong in this theorem which was used, this theorem by Glim. You have UHF algebra, which is very strong, and Krein-Milman does not even need the assumption of being an algebra. You just need some locally convex topology.
Mm-hmm. So is the Glim theorem an old theorem?
Sorry?
Is the Glim theorem is an old theorem, because in the talk,
Yes.
in the talk, yes, you refer to the Glim theorem. What is the reference for Glim theorem? What reference or what paper of Glim you are indicating to?
Oh, you have to check. Unfortunately, I didn't put the references, but I can check. I can check, but I don't remember. I'm sorry.
Okay.
So once you are checking, let me read an interesting comment from Dimitris, who is probably out of microphone.
Oh, Dimitri.
Yeah. Take any quantum isometry group of the closed unit interval. Then it cannot act transitively since the closed interval is not homogeneous.
Yes. Any quantum isometric group of the closed unit interval?
Yes.
Yes.
Yeah, but it's a command for a counterexample. But you are saying that something magic happens for the what, two-sphere?
So my question is that I don't know what I mean anything coming from a spectral trip. But quantum isometric group of the closed interval can it be counted as a non-commutative sphere? Because I was talking about the perturbation of the classical sphere. To be honest, I confess that I don't know what is the exact definition of quantum isometric group of the closed unit interval.
Okay, so should we wind it up, or do you still need to check?
Hi.
Hi, Dimitri. Oh, so you have a microphone.
Yeah.
Okay.
So I mean quantum in brackets, in the sense that any isometric group that can come from some spectral triple on the unit interval. So if you ask for it to act transitively on the closed interval, it cannot, because the endpoints, I mean, they're not the same as interior points.
Yes, the classical interval is not homogeneous. Yes. So your underlying space is the space of continuous functions on the interval, and you consider a quantization of this algebra. Yes.
Maybe yes, maybe not. I'm just giving an example that you should not always expect any isometric group of a spectral triple to act transitively.
No, but I think that the original question of Ali was about quantum sphere.
Yes, I was talking about quantum sphere, non-commutative sphere, because I was motivated by the round sphere, classical round sphere.
So when you say classical round sphere, do you mean the two-sphere?
Yes, two-sphere or every n-sphere with the usual Riemannian structure, the isometric group has a transitive action. So that was my motivation for asking that question.
But you're asking about the quantum one.
Yeah, exactly.
Yes,
He's asking if it pertains to the deformation.
Probably it can act transitively if you have a good spectral triple.
But you know, Dimitri, maybe one can use exactly your argument that when you look at, say, the Podlesh quantum sphere, it has one classical point and all other points are quantum. So that's not exactly the same. But then it is homogeneous, but for a quantum group, not for a classical group.
Yes.
Yeah. So, for instance, I couldn't, when I was defining quantum real projective spaces, I could not use the standard Podlesh quantum sphere, because there is no non-trivial classical group that can act on standard Podlesh, because this one point cannot be mapped non-trivially to anything else. So there is no Z2 action on the standard Podlesh quantum sphere. But then I went, of course, to generic Podlesh quantum sphere, which has the circle. And
I think the question was more like, can you give a notion of transitive action such that it makes sense to say if this is or not the case? I think this is...
Correct me if I'm wrong, your isometric groups are still classical groups. Right?
Yeah. And actually are related to quantum groups. The one constructed by Goswami.
Yeah. So Ali, your question would be even more interesting if you would change this ISO on quantum ISO. then I believe it's likely.
If the structure is somehow related to something, to some graph which is strongly but very strongly connected or something, then it should be homogeneous.
Yeah. But homogeneous for classical group, you mean?
I would say both. I would say both also for the quantum ones. If you have an action for a classical one and for quantum one.
I mean, of course, we are just speculating, but my gut feeling is that when it comes to classical, I mean, to this ISO, as JACOPO was discussing, then it might be yes, might be no, the answer to Ali's question. But when it comes to the quantum ISO, Goswami and others, And my gut feeling is that it's almost always naturally transitive.
Yeah, you have more isometries, so
Exactly.
more chances to connect
Exactly.
stuff.
Exactly.
So.
Yeah. So can we wind it up now, Jacopo?
I have a question.
Okay, go ahead, Tomek.
Okay. Sometimes this classical group survives even after quantization. For example, the non-commutative torus. Okay, you have an action of a classical torus there, which is contained in the isometries of the classical.
I don't know if I can tell you about this because I work in. Yeah. It's necessary.
How far this classical isometry group of the non-commutative torus is different from this canonical action of this classical torus.
Yeah, soon. You will see soon. I think in a month, I feel it.
Just keep on recording for months. So let's thank our speaker again.
Okay.
I stop recording.